Thank you. Can you bring another slide? So I'm going to talk about batteries. Let's recap some of the stuff we learned about in the energy section. From energy generation, how do you get to renewable? So we have source of solar, wind, nuclear, and hydro. And also, I also want to emphasize we need to learn about how to use waste heat as well. And this whole energy landscape also requires us to think about how to use energy efficiently, like LED, Steve mentioned, smart building. And a place very hard to decarbonize is actually transportation. So how do you replace gasoline without burning it using electric car, for example? At the same time, we need to deal with the energy, the environmental problem, CO2 emission, particle matters, PM, SOx and NOx, heavy metals, pollutants. So this is the whole, really the whole energy landscape right here. And if you look at these energy application areas and the generation areas, solar is doing very well from the cost of PV, and we have nice LED. The missing link is actually the energy storage. How to store the electricity let's see. So this is the missing piece right there. If you can solve this problem, how to store electricity, it can help with electrical transportation. It can help you to incorporate more, introduce more solar cells and the wind, this intermittent source into the grid. So this is the missing link. Our technology is not quite there yet. We are still quite far away. However, you start to see a promising situation coming up in the transportation sector. So now let's come to the energy storage. How do you store electrons? So I want to show you one slide of this, the learning curve we have in the past 40 years. The mobile phone was invented in 1973. So it's about 43 years now. This is experience you see from the left-hand side of the phone, really big. Do you know what's the weight of the first generation of mobile phone? Anybody has an idea? It's more than 1 kilogram per phone. And then the phone gets smaller and smaller. The smaller the phone you carry, the more it indicates the other guy really follow up with the cutting edge technology. However, in the past roughly 10 years or so, things change. The phone gets bigger and bigger and bigger. So what's happening? So if you look at the phone inside, right, this is the big piece inside right there you see, I highlighted. That's the batteries. It's actually the battery size more or less determine your phone size. The first generation of mobile phone, we use lead-acid batteries. It's very heavy, low energy density. And then we move on to nickel cadmium, nickel metal hydride, and then lithium ion. Lithium ion has the highest energy density. The phone gets bigger and bigger because we have more and more application, more and more app in the phone. We consume more power. We need a better size battery. Certainly, we want bigger display as well. So this is the technology we have seen in the past 40 years. Now, can the battery technology push to the degree we can use that for transportation, for the grid? So how far the battery technology can go? And one parameter you look at is energy density, how much energy you store per unit weight or volume. For the cell phone, what's important is the per volume. For the transportation, it's more important about the weight. Certainly, the volume is also important. The cost, cycle life, charging, discharging rate, and safety. So the question for the batteries, what are the key parameters you are really looking for? Looking at the status of technology right now, these three things are really what we need. Number one is we want higher and higher energy. Can we produce the battery 2 to 3 times higher in energy? So a car can run 2 to 3 times more distance compared to the current status. That for the Tesla car, that means from 250 miles to 500 miles per charge, or even 750 miles. With that, you can already beat the gasoline, the same or beating the gasoline. And then the second one is the cost. Steve showed you the curve. Tesla's Gigafactory will get you somewhere around $175 per kilowatt hour. We need lower cost. So can we reduce the cost by half or go to the 1/3? That really determines whether the electrical car can be accepted by the general public. The third thing is I want to emphasize, given the recent incident of Samsung mobile phone, is the safety. Can we make the battery intrinsically safe? It doesn't have the accidents. So if this can be solved, we are really looking into revolution in transportation, grid, and renewable. This is a big part of the sustainability and for the world. So now let's look at the science part. How do we store electrons? What's the fundamental questions? When we store electron, what's the consideration? We know electron has negative charge. If you put them together, they don't like each other, you cannot store a lot of them. In order to store a lot of electrons, you put in something with positive charge, that's called ions, metal ions. That's a positive charge. They recombine and they generate charge neutral. But oftentimes, electrons and this ion cannot simply meet together. You need to put on something we call a host materials. At the end of the day, electron is very lightweight. Your metal ions, the one you can find probably is not heavyweight either. It's the host materials that's too heavy. That's the overhead you pay in order to store electrons. So what are the choices right there? Looking at all the battery technology, the lightest element you want to use is hydrogen. If you can use hydrogen, that's perfect. However, when hydrogen takes in electrons, it's going to generate hydrogen gas. Very hard to store. You need to solve that problem. And the next one is lithium. Lithium ion is having the atomic weight of 7 times more heavier. However, it's the next lightest element you can find. And then if you go out, you have sodium, magnesium, aluminum, zinc, and lead. They all come up. They are going to become heavier and heavier and heavier. For magnesium and aluminum, it's actually a good deal because they are divalent charge or trivalent charge. One element, one atom can take on 3 electrons, maintain charge neutral. But the price you pay is they have a high charge. And then when they move in solid state, they are very slow. Electrostatic interaction with environment is very strong, so very hard to make it to work. And then what about the voltage? For a battery, you need to consider the voltage. It has something to do with electronegativity right there. For the hydrogen-based batteries, or fuel cells, you can call it, it's about 1.5 watt or below. Lead is about 2.1 watt. Lithium gives you the highest one. That's 4.5. That's because lithium is the most electropositive element you can find. So allow you to build high voltage battery. That's why cell phone, laptop use lithium. And it has this 4 watt right there for you to output enough voltage to operate your transistor. And the next consideration, of course, is the cost. From the cost standpoint, lithium is not a good choice. Right? Lithium is not a good choice. It's too expensive, $1 per kilogram. Hydrogen is the best one, virtually free. It can come from water. The other one, they're all low-cost sodium, magnesium, aluminum, zinc, and lead. They're similar. However, you have to consider, every time you put in an electron and you need one lithium, actually in the lithium-ion battery, the cost of lithium ion, the lithium, is only 3% of the battery cost. It doesn't matter yet for this consideration. But I'm going to come back to touch upon the availability of lithium later. So that's why lithium-ion battery has been dominating the whole portable power market. And then you say, how far I can push. Remember, I want 2 to 3 times higher energy. I want low cost, I want safety. Let's look at energy density first. And the graphite is used. Since about 40 years ago, lithium-ion battery was commercialized. And it can intercalate, having this layer structure. Lithium can go in and go out easily. It can store a lot of them. However, we are now already seeing the limit after this 40 years, about 30 years of development. And we need new material to store a lot more lithium ion in order to get more energy. We have choice of silicon and lithium metal itself. And silicon can store a lot of lithium. I'm going to show you in a future slide. And for the positive electrode, battery has two electrodes. One is negative, the other is positive in order to build up the voltage. These are the lithium metal oxide, three family of material: lithium cobalt oxide used in your cell phone and your laptop, lithium manganese oxide spinel, and lithium iron phosphate. Lithium iron phosphate is used a lot in the electrical transportation. We all use a limit right now, 150 milliamp hour per gram of capacity also. We want to look for a better choice, can store a lot of lithium. Sulfur is a very low cost material available in very large quantity. It can store about 10 times more lithium ion compared to the existing cathode. Its voltage is about half of the existing cathode. But the amount of energy you can increase is actually a lot by using sulfur. It's also very low cost. So this is the potential type of energy we can get to. If we use current technology based on carbon on the left, and we want to look for 3 times of the energy density, we actually have a choice using silicon combined with other type of cathode, silicon as anode. If you want to look for 6 times, it's also possible down to the fundamental chemistry level. However, we have not seen this technology being used in your real application. There's reason behind it. So the challenging is, past 30 years, 20 years we learn is you need to have a host, a stable host, in order for lithium and electron to come in, remain charge neutral during charging and discharging. The new material with very high capacity, there's too many lithium ions coming in. They start to come in and do really bad things. The first thing is chemical bond breaking. The host materials holding so many lithium ions, they cannot take it. Their chemical bonds are broken. And the second thing is host atoms move to very long distance. And the next one, complete structure change, big volume expansion. Existing battery material is less than 10% volume change in the materials level. But for the new materials, store a lot of lithium, they have 100% or more volume change. Volume change is too big, the batteries are not stable. So this atomic bonding scale broken, and the individual particle scale of material, they are also breaking, and also instability of interface. In the whole electrode level, if electrode is expand, the whole battery is breathing all the time. You are going to break the packaging, leaking out organic electrolyte, and it's not stable. It can cause accidents. So let me now emphasize, in the past 10 years, there are actually new aspects of battery research. Now try to tackle this problem. I want to highlight several examples in this talk. The first one, let me show you the advanced tools to watch battery operation. The first one is transmission electron microscopy. With this holder right there, now it's possible to apply a voltage, apply current, charging up your battery, and then watch what's happening inside transmission electron microscope. Let me show you a video. Maybe it runs out of batteries. So inside this video, we now have a way. Let's look at it. I think it does. Runs out of batteries. Can you play the video, the first one? So this is a silicon nanowire structure coated by, let's just play the first one. This is the second one now. Let's come back to the first one. You see when lithium going to silicon, the volume expands a lot. There's a copper coating on the surface. It's actually broken. So this volume expansion to about 400% of its initial volume. Let's look at this second one. This is let's go to next one with the particle. This is a silicon nanoparticle that's diameter is 800 nanometer in diameter. When lithium coming in, you can see that big particle start to swell bigger and bigger. Eventually, there's too big of a stress building up. This particle cannot take this stress and get broken completely. Once this particle is broken, you lose electrical contact, you lose materials, the battery will die. You see the particle now is broken up. Using a technique like this, we can identify how the materials is changed, what's the critical breaking size, to help us to design the right material to solve those problems. So these are the problems you see. For the very high capacity materials, it goes through this volume expansion from silicon particle become lithiated silicon, lithium silicide particles. And then it's going to be broken. Now the question is, how do you design the materials to overcome the breaking problem? And then how do you build stable interface between these particles and organic electrolyte? That's the research my group has been doing in the past 11 years at Stanford. So now let me show you the first generation of thinking, how do we overcome this problem? By having this first generation of silicon nanowire, their diameters are small enough, so once the volume expansion happens, they can relax the strain to outer surface, they don't break. So we showed, nanotechnology is really powerful to help solving the problem in the battery field. And we move on, we have the second generation core shell structure, having a stable core and a shell of silicon to store lithium, and then we produce the hollow structure, and the hollow structure can help relax the strain interiorly, inside, so to overcome the breaking problem better. So after these three generations, about 3 years of research, you recognize if you made a structure small enough, they will not break anymore. This looks easy. If you go to nanostructure, they will not be broken. However, the second problem is so hard to address. That is, every time you put lithium in, there will be volume expansion. Expansion will go towards outside, pushing the electrolyte. So once you take lithium out, they're going to shrink. So you don't have an interface to build a so-called solid electrolyte interface. So your battery will also die with cycle. You cannot go for 500 cycles for your cell phone. You cannot go to 3,000 cycles for your electric car. So in order to build a stable interface, several years ago, my group came up with an idea. I think this is a universal concept now. How do you solve a problem of this instability of interface? Let's look at the generation 4. We have actually a double wall hollow structure. The blue color is silicon. Outside is a mechanically strong layer. Once lithium coming in, volume expansion, you actually try to promote towards inside instead of outside. You leave empty space inside. So it doesn't push outside. You build a stable interface facing electrolyte. Now your battery becomes very stable. So we showed that in this publication. I consider that as a very important milestone in the battery research. So we have been through this. We have a lot of fun now. 10 years, we have 11 generations. I won't go into the details. With all this research, it's indeed very important to translate the science we learn, the materials we develop into the real world. In 2008, I founded a company called Ampere, so really try to push what are the remaining problems we can do. Now this company is taking this technology further. It's not trivial, certainly, to commercialize the technology. There's still many problems we need to solve. Likely, it looks like silicon has become very promising right now in the application space, in the commercial space. So, and with the success in silicon, in 2013, Steve come back to Stanford. I think I consider Steve come back to take vacation. Secretary job is really hard now. He's coming back to Stanford, a nice place. Every day is like vacation, and at the same time working on science to save the world. We want to tackle the lithium metal anode problem. Lithium metal is considered the holy grail of battery research because it has the highest charge storage capacity, and it has the lowest potential as anode, give you high voltage in the battery and then high energy. However, lithium metal has a notorious problem. It grows dendrite, short your batteries. So 40 years ago, 50 years ago, when people work on lithium-based battery, they want to make lithium metal to work, but they cannot. They could not do that. And they actually burn down the factory, the battery catch fire. Now we want to revisit lithium metal. Come up a new idea how to do that. Number one is to build stable interface. So we have a few ideas, looks very promising. And to build a stable host, construct a home to contain lithium metal. Now it's become more and more promising. Hopefully next 5 to 10 years we can solve this problem completely. So with that, for the high energy, I want to now come to the grid scale storage. You have seen grid scale storage because the scale is so big. So far, the grid scale storage is still dominating by this pump hydro. That's Steve's favorite technology. I'm showing you a much bigger scale right there, pumping the water. So pumping the water certainly is location dependent. How big of a lake you can build right there, that's questionable. So can you really use the battery technology for that? But now let me emphasize the scale of the problem. Every year, the annual production of our lithium-ion batteries, the total capacity of the whole world is only 35 gigawatt-hour. California alone can easily take all the battery yearly production of the whole world to do our grid scale storage. We can consume that, no problem. The Tesla's Gigafactory can only double the world production going from 35 to 70. So we have a huge need of grid scale storage right there. So this is the scale you need. This is the Stanford Stadium, football stadium. Very big, right? Can hold probably somewhere around 70,000 people. The world production of the battery can fill half of the stadium. So it's really big battery you need right there for the grid scale you can consider. So one idea how to do grid scale storage is to use liquid redox molecules solution. Instead of using solid state electrode, you can have a big tank to store this redox molecule. When you want to charge out your battery, you're flowing in, and then when you discharge, you flow in the reverse way. And vanadium redox flow battery has been considered. However, it's the cost that really the roadblock right now. The one reason is the ion selective membrane to separate the two liquid in the middle right there need to be ion selective. It's expensive. Naphthalene is the membrane to use. The second one is the limited solubility of redox molecule. That means your energy density per unit weight or volume is too low. Now, given all the investment you put in for the pumping, for the piping, for the tank, you want more energy coming out, otherwise your cost is too high. So what you really want is you want to remove the expensive membrane. You want higher energy density as well, even for the grid scale. In principle, grid scale is not limited by the footprint. However, from the cost consideration, the energy density can become important. So I want to show you one example. It's actually using a polysulfide redox molecule. Its solubility is 5 times of the vanadium redox. And then this polysulfide, the red color liquid, contact with lithium metal, forming this self-decomposition compound. It's a lithium ion selective membrane by itself. So you don't have to use expensive membrane anymore. And this one has about 5 times higher energy density compared to the vanadium redox flow. The sulfur is cheap. This has the possibility to give you a grid scale storage solution. And the remaining of a few minutes, now let me come back to the question about lithium, availability of lithium. Many people, including myself, doing sodium ion research, magnesium research, aluminum, right, zinc. Magnesium, aluminum, all these are cheaper. So is lithium a reserve become an issue? Let's look at the global reserve of lithium. We have 40 million tons of lithium reserve discovered. But this number is going up. Every year you discover more and more lithium reserve. This number is going up. Actually, in the past 5 years, the reserve doubled. People discover more reserve. So what does the 40 million ton mean right there? My colleagues right here might need to use some lithium to breed, the nuclear materials. Other than that, lithium will be used for the transportation batteries and also for the, making the airplane, the alloy to be lightweight. So let's look at Nissan Leaf. This electric car runs about 84 miles. It's only 4 kilograms of lithium inside. That means it can make 10 billion Nissan Leaf. Anybody knows now in the whole world how many cars we have in running? After about nearly 100 years of car commercialization history, how many cars are running right now in the whole world? So we have 1 billion cars also running. So now you have 10 billion kind of lithium reserve right there, not too bad, right? We can get somewhere for the electric car. And then in 2009 alone, the lithium production can allow you to produce 23 million Nissan Leaf. If you want expensive car, you produce 3 billion Teslas with this reserve. And if you still want more lithium, ocean has virtually infinite amount of lithium right there, 230,000 million tons of lithium. But the concentration is low, it's 178 ppb. How do you extract lithium out of the ocean with low cost? That's worth some consideration. So Steve and I actually have a code development project right now at Stanford. We try to develop technology with low cost to extract lithium out of the ocean. It looks very promising. For the grid scale, if you decide to use lithium, our world electricity consumption is about 4 terawatt. If I say I want to store the whole world's electricity for 6 hours, so that means 24 terawatt hour. Our now lithium reserve, global reserve, allow us to do 10 times more. We can store 240 terawatt hour. So lithium-ion technology will go very strong in the next 20, 30 years, maybe even longer, given this consideration. And then last minute, after this I will stop. It's about the battery safety. You have known about, in the past 20 years, what's the safety incident. Reason why is the Boeing 787, and as well as this hoverboard, and as well as Samsung's Galaxy phone. And can we really solve the battery safety problem? If our battery is low cost enough, high enough energy density, the next question the public will care about is the safety. So what's the fundamental reason why battery is not safe? This is the drawing of a battery anode and cathode. Inside, filling with organic electrolyte. They can be burned. So what happened in most of the instance is for some reason, you have a shorting inside. Whether it's due to the manufacturing defect or due to the overcharging, charging in the cold weather, or the, the car accident. So you have this battery shorting. Next thing that happens is this, it releases electricity very fast. This releasing of electricity causes the battery to heat up to about 100 degrees C. At 100 degrees C, bad things start to kick in. You start to have exothermic decomposition of solid electrolyte interface. That's the decomposition compound on each of the particle surface. At this moment, it's still not too bad. You can damage your battery, but it doesn't cause the safety, burning yet. But once the temperature heat up to about 180 degrees C inside the batteries, you are going to have exothermic reaction between your cathode, that's lithium metal oxide carrying a lot of oxygen, reaction with organic electrolyte. It goes through a thermal runaway. At this moment, you cannot stop the battery heating. It will just automatically go, catching fire and cause explosion. So we ask the question, under no circumstances can you really make the battery not go over 180 degrees C, ideally not even go over 100 degrees C. This is an idea. We come up with an idea like this, working with my colleague, Professor Chen Bao in chemical engineering, is can you coat your metallic foil or current collector with a layer of insulating polymer, blue color, inside with these nickel nanospikes. If the battery heats up, volume expansion of this polymer, they're going to pull open this nanospike, and then you cannot pass current through that. Even this shorting happening, you prevent the direct shorting from current collector to the current collector, taking this electron out of the battery materials. So we actually developed such a coating with nanospikes of nickel, now in this polymer, polyethylene or polypropylene. And now you can see this is the key data, is the resistance of this polymer film versus the temperature. And room temperature is a really good conductor, metallic conductor. And then when the battery heats up, let's look at the green curve, to about 95 degrees C. There's a sharp transition, and this layer become a perfect insulator. The resistance change by 8 orders of magnitude. So at this moment, the battery just shut down itself without releasing the electricity. You can prevent the bad things happen. So this is an indication, battery and the charging, discharging with capacity coming out. Once it heats up, you get to the zero capacity. You cannot take the electrons out anymore. We need to do more testing. And so far it's in the lab as a small battery cell. We need to do a big cell and a realistic cell for use for the transportation. So at the end, now let me summarize. This is the goal we try to get to. If we get higher energy density, 2 to 3 times, that really means your car. If it's a Tesla, it will go 500 miles. If it's a Nissan Leaf, you can go from about 100 to 200 miles. And with the high energy, the same manufacturing cost, that also made the cost per energy reduced by 2 to 3 times. That's the most powerful knob you can tune to reduce the battery cost. We need new ideas for the battery safety. So under no circumstances, the battery will catch fire to make it completely safe. And this has a really huge meaning for transportation, to renewables, to solar and wind. Thank you very much for your attention.